Question 1. For this feedback control system, we require to have a 10% maximum overshoot and settling time should be 1.5 seconds or less. We are asked to find constants K1 and K2 to meet the requirements. To solve this problem, we start simplifying the inner loop containing G2 and H2 and determine the transform function relating C and Q. This results the equivalent block diagram which is showing here. Now again we find the overall system transfer function relating output C and R. Comparing the obtained transform function with the standard second order transform function here, we can conclude that 2 zeta omega n equals 1 plus K2 and omega n squared equals 0.1 times K1. To determine the damping ratio zeta, we can use the overshoot formula. Substituting 10% MP into the formula, solving for the zeta, we get zeta as 0.591. And to determine the natural frequency omega n, we can use settling time proximate formula with 2% tolerance, 4 divided by zeta omega n, which it results 4.51 radian per second. As a reminder, the settling time is defined as a time for the response to reach and stay within 2% of its final value. Now by substituting omega n into omega n squared expression, we calculate K1, and by substituting omega n and zeta values into the 2 zeta omega n equation, we find K2. By the way, if you like what you are watching, please hit the like button and also subscribe to the channel. Now back to the video. Question 2. For this non-unity feedback system, we need to find the constant K for a desired steady-state error as 0.15 and a step signal input with amplitude of 0.2. First, we determine the overall system transfer function. Here, the error signal EA of S is defined as input R of S minus the system output Y of S. The output Y is the system transfer function multiplied by the input R. And here we rearrange the expression, and the Laplace transform of input step signal is its magnitude divided by the operator S. The steady state error in Laplace domain equals limit when S goes to 0 of S times the error E of S. Finally, we substitute the input signal and simplify the expression and solve it for constant K, which we obtain K equals 4. Question 3. For this control system, we need to find the value of K, which the closed loop system is stable. First, we need to find the relationship between the output Y and input R. To simplify this block diagram, we can remove the takeoff point to behind block G. And at the same time, a block 1 over G is placed in the return path. Now we simplify this inner negative feedback block diagram, which it becomes 10 over S plus 12. So if you look at this bottom block diagram, you can see that GSC and G are in series and they can be replaced by their product. Again, the transfer function of this negative feedback can be calculated as shown here. The denominator of the transfer function gives us the characteristic equation. For this second order system to be stable, all coefficients must be positive. So the coefficient 13 plus K and also 12 plus 2K should be greater than 0. This will give us two solutions, K greater than minus 13 and K greater than minus 6. So for both conditions to be satisfied, then K must be greater than minus 6. Question 4. For this unity feedback control system, find gain margin GM and phase margin PM. Gain margin GM is the gain at the phase crossover frequency, and phase margin PM is the phase at the gain crossover frequency. First, we determine the loop transfer function LA of S and substitute j omega into the LA of S. Next, we determine the phase angle of LA of j omega. To find the phase crossover frequency omega APC for GM, we set the angle of LA of j omega PC to minus 180 degrees. After solving for omega, this implies omega PC is at infinity. And we determine the magnitude of LA of j omega at phase crossover frequency. As you can see here, when omega APC approaches to infinity, then this magnitude goes to 0. Therefore, the gain margin GM goes to infinity. Next is to find the gain crossover frequency omega AGC for phase margin. So we set the magnitude of LA of j omega equal to 1, which it gives us the gain crossover frequency omega AGC. Then we substitute the omega AGC into the LA of j omega to find its angle. Finally, the phase margin is 180 degrees plus the angle of LA of j omega C. Question 5. For this unity feedback control system, the velocity constant is 120 and the damping ratio zeta is 0.69. We need to determine the value of Kp and Kd for the PD controller. To solve this problem, first we use the velocity constant formula to find the relationship between Kp and Kd. Substituting the Kv value and solving the limit results the value for Kp. Then we determine the closed loop transfer function. Now comparing denominator, which is the characteristic equation, with the standard second order system, we can say that the omega n squared equals 30 kp and 2 zeta omega n equals 7 plus 30 kd. Substituting found kp gives us the value for omega n, and substituting zeta and omega n results the value for kd. Question 6. For this unity feedback system, find the constant K so that the closed loop system is marginally stable. First, we find the characteristic equation. The characteristic equation is obtained from the closed loop transfer function, and it is found by setting the denominator of the closed loop transfer function to 0. Then we construct the Routh table. The Routh table is a structured array formed using the coefficients of the characteristic polynomial. The first row corresponds to the coefficients of s in power of 3 and s in power of 1, which are 1 and 32. The second row contains coefficients of s in power of 2 and s in power of 0, which are 12 and k. The third row, s in power of 1, is calculated as 12 times 32 minus 1 times k divided by 12. And for the fourth row, s in power of 0, since we have a 0 at the third row here, we just bring this coefficient, which is k, in the second row, to the fourth row here. For marginal stability, a row of zeros must occur in the Routh array. This happens when here the s in power of 1 row becomes 0. So, the denominator of this equation must be 0. After solving it, the constant k, for which the system is marginally stable, is 384. By the way, if you like what you are watching, please hit the like button and also subscribe to the channel. Now back to the video. Question 7. For this non-unity feedback system, the damping ratio is 0.4. We are asked to find the value for constant k and then determine the settling time, peak time, and maximum overshoot. First, we find the closed loop transfer function. Now we compare the transfer function with the standard second order form. From denominator, we have 2 zeta omega n equals 13, we substitute the damping ratio zeta and get omega n equals 16.25 radian per second. Again, from the denominator, we have omega n squared equals 12 plus k. After substituting the omega n, we obtain k approximately equals 252. For a 2% tolerance band settling time, we use Ts equals 4 divided by zeta omega n formula. And by substituting values in, we get settling time as 0.615 seconds. To calculate peak time Tp, we use pi divided by omega d formula. And by substituting the values, we obtain TAP as 0.211 seconds. And finally, for the maximum overshoot in percentage, we use this formula, which it results MP approximately 25.38%. Question 8. For this unity feedback control system, we need to find the value of constant K, which makes the gain margin 15 dB. The first step is to determine the phase crossover frequency, omega APC, by setting the phase of the open loop transform function gh of j omega to minus pi or minus 180 degrees. Since we have a unity feedback, then h equals 1. So the phase of g of j omega is given by this expression. Remember, the phase of constant k is 0 and phase of j omega is 90 degrees. Solving this equation for omega will give us the phase crossover frequency. Omega APC equals 7 radian per second. Next, we find the magnitude of the open loop transform function at the phase crossover frequency. After substituting the omega PC, we get k over 588 as a magnitude of open loop transform function. This is the relationship between gain margin in decibels and magnitude at the phase crossover frequency. Substituting the given 15 dB gain margin, we obtain the relative magnitude. And with that, we can calculate the value of constant K. Question 9. For this unity feedback control system, the damping ratio zeta is 0.68 and damping oscillation omega d is 13 radian per second. We need to find the value of constants K and M. To solve this problem, first we determine the closed loop transform function relating output C to R. By comparing this transform function with the general second order transform function, we can see that 2 zeta omega n equals 4 plus m and omega n squared equals 2k. Here is the relationship between damping oscillation omega d and undamped natural frequency omega n. By substituting omega d and zeta into this formula, we find the omega n in radian per second. Now by substituting omega n into the 2 zeta omega n expression, we calculate m. And also by substituting omega n into the omega n squared expression, we determine the value for constant K. Question 10. For this non-unity feedback control system, we are going to find constant K so that the closed loop system is stable. So first we determine the closed loop transform function. A closed loop system is stable if all roots of its characteristic equation have a negative real parts. The characteristic equation is found by setting the denominator of the closed loop transform function to 0. For stability, the pole S must be negative. So the minus 5 minus 20k must be less than 0, and we solve it for k. Thanks for following along. I hope you enjoyed this video. You can find more quiz and solve problems on this topic in the playlist and post section of